Okay, so I'm going to start with taking a moment to look at um, dot structures. Oh, there's another person. Hello, Nicole. All right. So I'll kind of move this thing over so I can get my buttons. There you go. Okay, so you've had a chance to look at the dot structures from chapter 3, but I know we have kind of a variety of backgrounds, and last week a couple of you were saying that you weren't really familiar with them. So what I'd like you to do now, and I'd like you to, in that chat, kind of tell me where you fit in this question of how you're doing on the dot structure. So I've got everything from, you feel pretty confident with them, you don't really need any help, you're okay on some of the easy ones, but you need help with the tricky ones. You can only do things as long as they don't have double bonds, or you just don't even know how to get started. So kind of let me know where you are on dot structures. All right. So nobody's perfect on them, but we got a little bit of a range of where people are at the moment. Okay. So what I want to do is I'm just going to briefly go over, oops. Oh, yeah, that's why I did that. Okay, I'm going to briefly go over a couple of things, and then we're going to work on a couple of the examples. So the first thing I always like to do is to talk about why we need to do this. And one of the central things for dot structures is to help us to know what the shape of the molecule is. And the reason why we want to know the shape of the molecule is to know if it is polar or not, because whether or not something's polar really affects how it reacts chemically. And so we're going to use the dot structures to kind of lead us that way. And so the main thing we're going to get out of this is how many lone pairs, and those are the leftover dots that are not part of bonds, how many lone pairs are going to be on that central atom. And that's what we're going to be looking for too. Now, you can do dot structures with, really big molecules, but we're going to stick with ones that only have one central atom and everything else is attached to it. So don't worry about some of the more complex examples you might see, whether you're looking in the book or online. We're just going to stick with the simplest examples. I don't like to use dot structures with ionic compounds because usually we use the dot structures to show sharing of electrons, and ionic compounds don't share electrons. They transfer the electrons to the other atom. So we're just going to stick with nonmetals in our structures. And what we're going to need to do is know the total number of valence electrons for each of our atoms. So the way that we count our valence electrons is by looking at the periodic table. And so we've got kind of a brief version of the periodic table here. It's going to show us something else in just a minute. But what I had indicated the last time we talked is that you can just count the number of elements in that row until you hit that element. So if I'm looking at beryllium, Be, and that's on the left-hand side, it's the second element, so it has 2 valence electrons. If I'm looking at oxygen, I have to kind of jump over that gap, but it is the 6th element in its row because I have lithium, beryllium, boron, carbon, nitrogen, and then oxygen. So it would have 6 valence electrons. Now there are elements near the bottom that have that big block of transition metals, and we always skip over the transition metals. So it turns out that oxygen has 6 valence electrons, and so do all of the elements underneath it, sulfur, selenium, and tellurium. Carbon has 4, so does silicon, so does germanium, so does tin. So if I can figure out what the number of valence electrons is in the top row, then I can figure out what it is for the lower down elements as well. Most of the elements we're going to work with are going to be near the top anyway, but if you ever have one that's further down, all you have to do is figure out what it would be for the topmost element in its row. So the other thing that this shows is what's called electronegativity, and that plays a really important role in chemistry because this is the ability of the atom to draw electrons to itself, especially when it's in a bond. And so you can kind of think of a bond as being a game of tug of war, and the electronegative elements are the stronger ones that can pull those electrons closer to them. And in the first chapter, there was an image that showed the size of the atoms, and we talked about how it's kind of counterintuitive, but as we go across the rows, instead of getting bigger, they actually get smaller. So lithium, element number 3, is a lot bigger than fluorine, which is element number 9. And so the reason that fluorine, element number 9, is able to draw electrons so close to itself is in part because it's so small. So the electrons are a lot closer to the nucleus where the positive charge is, and it's also because there's a bigger positive charge. So what you need to take away from this picture is that fluorine is the most electronegative, so it's got the 4.0 on it, and it's the tallest bar on here, and everything else is smaller than that. And for the most part, it's just kind of a gradual, the farther you are away from fluorine, the less electronegative they are. And so we're just going to kind of use that idea. We're not going to worry so much about the numbers. We're just going to, think about, okay, if I have oxygen, that's right next to fluorine, so it's more electronegative than, say, carbon, which is farther away. So the one exception that you'll see is hydrogen. And just like last week, I said that's kind of a problem child, is that hydrogen really fits in closer to carbon than it does over there by lithium. So that's the one that doesn't follow the trend of how far away it is. So any questions about electronegativity before I move on? All right. So I've got some step-by-step rules here, and these are pretty similar to what you'll see in the book. But what I like to do is first start by counting the total valence electrons, because we're going to need that to compare to how many dots that we have. And then you're going to put the least electronegative atom in your formula in the middle. And so choosing which atom goes in the middle is kind of central to figuring out how to do your dot structure. Fortunately for us, when we have a chemical formula, usually that first element is the one that goes in the middle. So I'm going to back up to our electronegativity picture for a second. Oops, that direction. And then I'm going to type in the chat window if I'm looking at NH3. And I didn't do that to everyone, so let me do that, NH3. So you can kind of see the formula there in the chat window if you look at it. I have two different elements, nitrogen and hydrogen. And I just realized this was kind of a bad example to start off with. So let me change that to NF3, and then we'll come back to NH3. So NF3. So between the two of them, fluorine's the most electronegative, so we're going to put nitrogen in the middle. And that's how we'll choose our starting point. If I was going to look at, say, SO2, S is it's diagonal from fluorine, but oxygen is right next to it. So we're going to consider right next to be closer than diagonal. And so sulfur is going to go in the middle. And if you're ever in doubt, you're just going to pick whatever that first element is. So if I were looking at, let's say, SiH4, would the silicon or the hydrogen go in the middle? What do you think? So what you're looking for is which of those elements has the smallest number on the electronegativity.
So silicone would be in the middle, right?
Yes, silicon would be in the middle. Very good. And again, you know, when you're in doubt, you're going to put silicon in the middle. So back to our problem child, hydrogen. Hydrogen can only form one bond, but if you're in the middle, then you necessarily have to be forming at least two bonds. So we're going to put the least electronegative element in the middle unless that element is hydrogen, because hydrogen just can't go in the middle. So if we go back to NH3, even though hydrogen is less electronegative than nitrogen, hydrogen can't go in the middle. So we have to stick the nitrogen in the middle. All right, so once you have your element that's in the middle, you're going to surround that element with the symbols for the other elements. And usually there's just one, but sometimes we can have more than one attachment on there. And then you're going to place a bond between the two of them. And a covalent bond is always two electrons. And that's important to remember if you're drawing a line. So some people do it with dots, and that makes it easier to count the dots. But if you are, if you're having a whole bunch of dots on there, it can get kind of confusing seeing all of those dots. So you're going to place a bond between the central atom and each of the surrounding elements. And then you're going to remember that when you're counting the electrons that are in these bonds are shared between both of the atoms. So we're trying to fill up our octet, and so they count for both of them. So if I look at, this is an example of, two hydrogens. So a hydrogen atom is a proton and an electron. We have each of those, and each of them only has one electron, but when they bond, I can count both of those electrons for both atoms. So if I were counting these dots, I would say each atom has two dots. Each atom has two electrons. Okay, so that's how we're going to be counting things, is that if I have a bond between two atoms, both of those electrons count for both atoms. All right, so I'm going to pull up an example here. Let me go to the whiteboard. Come on. There we go. All right, and so I'm going to take the example of our silicon hydride, and let me choose a color that's a little easier to see. There we go. Okay, so we have silicon hydride, and we said silicon is going to go in the middle because, well, first we're going to count our valence electrons. So silicon has 4 because it is in the 4th column over, and hydrogen has 1, but there are 4 hydrogens, so I have to count that 1 electron 4 times. So I'm going to say 1 times 4. So this gives me a total of 8 electrons. Then I'm going to put my silicon in the middle because it is the least electronegative, and I'm going to put my hydrogens all the way around it. And so we generally try to get these as if we are looking at the 4 corners, but I'm not doing a very good job of centering things. So I've placed the 4 hydrogens all the way around it, and then I can put 2 dots, or I can do 2 bonds. So I'm going to start with just doing dots. So I've got 2 dots here, 1, 2, 2 dots here, 2 dots here, 2 dots here. So once I've done that, what I want to make sure is that every atom has an octet. And so the octet rule for most atoms is I'm trying to get to 8 electrons, but again, hydrogen's always going to be a problem for us. So hydrogen only wants 2. So I'm going to look at all, okay, I'm going to look at all of the electrons, all of the dots surrounding hydrogen. And so right now, even though it's sharing those with silicon, it gets to count both of those for itself. So it has 2. And if I look at each hydrogen, I'm going to see the same thing. Each hydrogen has 2 electrons. So any other element we would say, oh, that's not enough, we need to do something else. But hydrogen, that's fine because it only has that very smallest shell and can only fill 2 things. Now we need to count for silicon. And so if we look at silicon, it has 2, 4, 6, 8 electrons, and so it has 8. So right now all of the atoms are happy, so we don't need to add any extra dots. So the next thing we're going to do is we're going to compare that to our original number of dots. We said we have 2, 4, 6, 8 dots, and we had 8 valence electrons, and they're equal to one another. So great, everything worked out perfectly. So that's kind of a simple example. So now what happens if they don't equal one another? And I'm going to kind of do 2 things at once here. One thing would be if we have an ion, and the other thing would be if they're not equal to one another. So we're going to look at the example of the nitrate ion. So you might remember nitrate is NO, and then it has 3 of these. Oops, try that again. 3, and it has a -1 charge. So when we're counting the electrons for this one, this can be a little bit tricky. With this, we're going to count nitrogen is 5. Now, does everybody see how you get to 5 valence electrons on nitrogen? That's where we have in the row for nitrogen, lithium, and then beryllium, and then there's a big space, and then boron, carbon, nitrogen, oxygen, fluorine, and neon. So as we're counting the elements, 1, 2, 3, 4, 5, it's the 5th element. So for nitrogen, we count 5. For oxygen, how many would there be?
6.
6, because it's the next column over, and we're going to count that 3 times because oxygen appears 3 times in the formula. And then we have this negative charge. So remember that negative charge is coming from an extra electron that's being added. So I'm just going to put a lowercase e for electron. There's 1 extra electron. And so what that means is that we've got 6 times 3 is 18, plus 5 is 23, plus 1 is 24. We have 24 total electrons. Okay. So which of these elements am I going to put in the middle, the nitrogen or the oxygens?
The nitrogen, right?
The nitrogen, because it's the farthest from the fluorine. Very good. So I'm going to put the nitrogen in the middle, and I'm going to surround it with the oxygens. And I've got to remember that I'm only surrounding it with the number of oxygens that are present. So I'm not going to put them all the way around. I'm not going to put 4 like I did with silicon. I'm only going to put 3. So I have my 3 oxygens. Then my next rule says I'm going to start putting in some dots. And let me switch this back here. All right, so each of those dots, or each of those pairs of dots, represent what's called a covalent bond. But unlike with my silicon hydride, now I need to fill out the octets for everything else. So if I'm looking at oxygen right now, it only has 2 dots and it wants 8. And even the nitrogen in the middle has 6 dots and it wants 8. And so I'm adding extra dots, and I do them in pairs, and we call these lone pairs. Sometimes we call them non-bonding pairs because people don't like the sort of contradictory language of saying it's lone, but it's a pair. But they're non-bonding. So I have 2 extra ones on nitrogen, And then I'm going to put extra ones on each of the oxygens until they have their 8 electrons. This would be a lot simpler if it would just let me do a dot, but it won't. So I have to kind of draw a little bit. So if this were all I had to do, then counting up the valence electrons wouldn't matter. But if we count these electrons, I'm going to have, starting on the left oxygen, 2, 4, 6, 8. And I'm only going to count the bonding pairs once. I'm not going to count them twice. So there's 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. But we only have 24 electrons available. So I've drawn more electrons than I'm really allowed to use. So if I have more dots shown than electrons available, if my total electron count is smaller, what I need to do is form multiple bonds. And the way that you're going to do this is you're going to have to remove 2 lone pairs and replace it with 1 bond. So 2 lone pairs is 4 electrons. We're going to take away 4 of those electrons, and then we're going to replace it with a bond. Now we only want a bond between the central atom and one of the extra atoms. So one of those lone pairs is going to come off of the central atom. So I'm going to take the lone, there we go, we'll color over that. Okay, so we take the lone pair off of the nitrogen, and then we can pick any of the oxygens, and we can pick any of the lone pairs on them. So I'm going to just pick the bottom one just for fun. So we'll take that one away. So this means that when I replace it, I need to bring my nitrogen, my oxygen back up to an octet. I need to have 8, so I need to put the bond in between those 2. I can't put the bond someplace else. Okay, so this area is a double bond. This is a double bond in here. So there's 2 bonds, and are 4 electrons there. Okay, so I'm going to count my electrons. I have 2, 4, 6, 8. Oh, let me put the spotlight back on. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've matched my total. And then I need to make sure that, okay, if I've matched my total, do I have the octet rule followed for everything? So we have to have both of those rules. So my oxygen here has 8. Oops, stay put. My oxygen here has 8. My oxygen here has 8. And my nitrogen has 8. So it's happy. Now, one last thing that we need to do, because this is an ion, and this is a little bit nitpicky, but it is important because we have some ions and some compounds that look very similar to one another, is that we need to indicate that this is a charged compound. We need to show that there are extra electrons on here. And the way that we do that is we just put off to the side our -1 charge. And sometimes, just to make it clear so it doesn't get mixed in with everything else and lost in what's going on, we might put a bracket around the picture and put the -1 to the side, or sometimes people will just put a small L around the number like that. So either way is fine. But those are kind of some of those points on there. So questions about dot structures. Okay, so I do have on Canvas kind of a step-by-step in there as well that you can follow. And as some of you have indicated, there are definitely sites online that you can go to that will walk you through some of those things as well. All right, so I'm going to go back to my PowerPoint, and I need to minimize this. Okay, so we said that the reason we're doing the dot structures is to start looking at polarity. And the reason why this matters is because when we have something that is non-polar, then it's going to mix really well with other non-polar things. So most of the molecules in air are non-polar. Oxygen, nitrogen, both of those are non-polar. Argon is just an atom, it's non-polar. Carbon dioxide is in the air in a small amount and it's non-polar. So all of those molecules mix together really well, and you don't end up with like a layer of oxygen separate from a layer of nitrogen, which is really good because we can breathe wherever we are in the room. And then if I have something that's polar like water, it's going to dissolve other polar things. And only polar things are going to dissolve ionic compounds. I'm not going to get into the details of which ions dissolve and which ions don't, but oil isn't really going to dissolve things like salt, but water can because water is polar. And then we also know that if they're not alike, they're not going to dissolve each other really well. So, we always know oil and water don't mix. If you've ever had your car washed and splurged on having the wax put on your car, you may have noticed that when you do get water on it right after there's wax on it, the water will bead up and roll right off. And that's because the water is repelled by that oil. So then the question is, how do we know if there are polar bonds? So the first thing that we look at is, are they the same element? Or if they are the same element, like in this picture, hydrogen and hydrogen, then it is not polar, because it's like identical twins playing tug of war. So they have the same strength, and so it's just going to be equal both ways. Now, if they're very different, if I have a metal and a non-metal, they're so polar that we call them ionic. So if you ever see a metal as part of a bond, whether that's a metal that we typically think of like iron or aluminum, we know those are metals, or if we have something that is just on the left-hand side of the periodic table, sodium, lithium, calcium, those way over on the left-hand side are always metals. If I ever see a metal, then I know I've got an ionic bond going on there. Most of what we'll look at will have two nonmetals. If they're not the same, then I can have a range. And so I can have something that's just marginally polar. And so that might be like if I had the hydrogen and the carbon. And the way that I know that it's very marginally polar is by looking at the difference in the numbers. And I can't remember if I put that back here. I didn't. I'm going to have to go back up. Sorry, I'm flipping around here. So if we look at carbon and hydrogen on the periodic table here, you can see the numbers on them are very close, 2.1 and 2.5. Okay, so the difference between them is less than 0.5. So that tells us that, yes, it's a polar bond, but it's just very slightly polar. Whereas if I look at something like carbon and oxygen, 2.5 versus 3.5, that's a difference of 1. And so that's something that I would call a very polar bond. So we just use that difference to kind of tell us, okay, are we talking about something that's slightly polar or something that's really, really polar? I'm not going to ask you to make that numerical difference there. The main thing that we're going to look at is, do I have different elements? So if I have different elements, it's at least slightly polar. So then the next thing we have to look at is the shape of the molecule. Because if I have different elements, but they're balanced out, like on the right-hand side here with carbon dioxide, each carbon-oxygen bond is polar, but they're polar in such a way that they are exactly opposite one another. So we say that that is a non-polar molecule. So what we're looking for is symmetry. So it's a perfectly symmetric molecule. It's completely balanced out. If we look at the left-hand side, the water molecule is bent. And so we have the same kind of structure with one element in the middle and two other elements to the side, but because it's bent, they can't balance each other out perfectly. And what causes that bending is those lone pairs. So that's why the dot structures were important, was to see, are there lone pairs on that central atom? So it's not a hard and fast rule. If you go on and take other chemistry classes, then you'll see that there are some exceptions to this. But a really good rule of thumb is that if the central atom has only one element around it and there are no lone pairs, it's going to be nonpolar. If the central atom has lone pairs, it's probably polar. Okay, so if you're looking at a molecule rather than just a bond, one of the things you want to look at is, are all the outside atoms the same? And in this case, we have one oxygen and two hydrogens. So if I have different elements on the outside, then it's probably polar. So there are very few examples of this that I will show you, but if you ever see that, different elements tell us it's probably polar. So the oxygen is really good at drawing electrons to itself. The hydrogen is not very good at drawing electrons to itself, so they're not balanced. Not balanced means polar. All right, so no lone pairs means nonpolar. Lone pairs means polar. Different elements mean polar. All the same elements, probably nonpolar. So we have the nitrogen in the middle there with 3 hydrogens. We have the 2 dots on the nitrogen. That tells us it is polar. Okay, so looking at these 3 examples, the one in the upper left-hand corner is methane. It has a carbon with 4 hydrogens. So do you think that one would be polar or nonpolar?
Would it be nonpolar?
It would be nonpolar. All of the elements around it are the same, and the carbon has no lone pairs. Okay, so let's look at the bottom then. We have a nitrogen with 3 fluorines on it. Is that going to be polar or nonpolar? So all of the elements around it are the same, which is the first indicator, but the second indicator is, are there lone pairs? So those 2 dots on the nitrogen tell us that probably it's going to be polar. So if you ever see dots on the central atom, that means polar. All right, and then what about the one on the upper right-hand side? So looking at the carbon atom, don't pay attention to that extra hydrogen there, just look at the carbon atom. So it doesn't have any extra dots on it, but does it have all the same element around it?
No, so it would be polar, right?
It would be polar, exactly. All right. So, of course, we have some things that are in between, and important chemicals for a lot of different reasons are called emulsifiers that have polar regions and nonpolar regions. And so organic compounds have lots of carbons, and because there's so many carbons, a lot of times rather than writing out each C, we'll just do a zigzaggy line where each corner is a carbon. So this molecule, oleic acid, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and I forgot this one, 18 carbons on it. And so that whole area where there's just a bunch of carbons and hydrogens is a non-polar region. But where the oxygens are is polar, because remember, oxygen and carbon are very different electronegativities. And so what happens is that if I have something like this, where I have both oil and water, the oil parts will attract themselves to this long chain to the right, and the water will attract itself to the oxygens on the other side. And so we can actually get the oil and the water surrounding the same molecule. And that's how we can, one example might be wash our hands, where the water is going to be attracted to that oxygen end, and the oils are going to be attracted to the other end. And so we're going to be able to mix those things and wash them off of our hands. Another place we use things like this would be in food, where you might want to be mixing, say, butter, which is really an oily or fatty substance, with sugar, where sugar dissolves really well in water. It's also very polar. So those are things that that don't mix together really well. And so we use an emulsifier. That's why we add the eggs. Eggs have molecules that are really good emulsifiers and allow those things to mix. If you ever use lotion, lotion has water in it to make it easy to spread across your skin, but it's also got oils to help seal in that moisture. So it also has an emulsifier in it to keep those things mixed together. So sometimes we even call something like lotion, we might call that an emulsion because it is a mixture of oil and water with an emulsifier. So a really, really, really important kind of emulsifier is what's called a diglyceride. And I know this looks like a really big and scary molecule, but I just want to point out that it has, part of it has a whole bunch of oxygens. And so you can, on the right-hand side, see a whole bunch of O's in here. And then we have these long chains coming out of it. The green and the blue are really long chains. And what we typically will do is just draw a circle for the part that has lots of oxygens, and then we'll draw lines coming out for the parts that have lots of carbons, the non-polar regions. So I kind of want you to keep in mind this picture on the left-hand side. The circle part is polar, and the straight parts are non-polar. So remember, our polar part, the circle part, loves water. So that's why we've got the heart-eyed emoji here. And then the lines coming out do not like water. They don't mix well with water. Sometimes we say they're hydrophobic. Okay, so what happens when you get a whole bunch of these things together? So if there's just a few of them, the non-polar regions will kind of stick together, or the polar regions will kind of stick together. So we get what's called a micelle. And this is how we might have fat in milk. So remember, milk is mostly water, but you can buy milk that is fat-free or 2% fat, or whole milk that has about 4% fat. That fat stays in there because of these little structures here. So we'll have these micelles that trap all of the fats inside because of all of those little sticks sticking into the middle. But what's really more important is that they can form this, what we call lipid bilayer, where they can sort of get across from one another and have their little legs tangle in with each other. And both sides sticking out are going to be polar. And so if you make that into a ring, we've got the inside that's polar and the outside that's polar. And that's how we form a cell. That's how you can have any cell in your body that has water on the inside, but also water on the outside. So most of your body is made out of water. This is how we separate the different parts of your body from one another. This is why you're not all dissolved inside of yourself, is because we have these layers here. And so that's what's really, really important about understanding polar versus non-polar, is that this really is what makes life possible. And now if I want to get something from the inside to the outside, it has to pass through that non-polar region. So I have to have something that can get close to these polar things, but can also get through this non-polar area. And all of the rules that kind of go along with, you know, is it big enough? Is it polar enough? Is it non-polar enough? That's what dictates how our cells work, and how, you know, we can maybe take in sugar and make that, turn that sugar into energy. That might be how we can, you know, have our nerve cells contract in order to move. So all of those things are related to this idea of having a polar and a non-polar region. And that's where that really gets important. And your book doesn't really go into that in much detail, but that's really kind of the crux of understanding this.